Hi, folks. We'll just give it another minute here if you're on board. Just another minute or so to see if any stragglers end up joining, and then we'll begin.
I think we are good to start, Dave.
Yeah, I think so too. Okay. Welcome. Good afternoon, everyone. Thanks for joining us. Joining Nuno and I today and offering us an hour of your time for what I hope is an interesting topic. Looks by the popularity of the registration that it is, that there's a lot of people in our HVAC world interested in this presentation about adiabatic humidification in cold climates. I'm David Ball. I'm the Northern Regional Sales Manager with Condair, which you may or may know formally as Nortec Humidification. I'll introduce my colleague in the corner here on screen. Introduce him in a minute. That's Nuno, but him and I will be bouncing back and forth a little bit today. First, I wanted to touch on how this presentation topic came about. I've been in the HVAC world for about 15 years now, with Condair for 10 years, and as a rep firm or part of a rep firm for about 5 years in the Ottawa area where the factory is based, Condair factory. And through that time, it's kind of been easy to see how important, that's for me, and I'm sure for you as well, how important energy has become and how important it is, whether you're a business owner, an architect, an engineer, a contractor, etc. It's not a buzzword anymore. It's energy is really a day-to-day word and a part of our day-to-day lives in the HVAC industry. So trying to apply that to my world as an RSM for a humidifier manufacturer, it's pretty easy to see how often adiabatic humidification is being used and watching how successful the results are when it's used correctly. But that's kind of been normal for me because that's my job, right? I work in the humidification world, so yeah, I hear about it every day. What was a little harder to see or discover was exactly where adiabatics were being used or being used successfully. And so I started to dig into the data and the history that I had available to me, or that I have available to me. And it's noticeable that adiabatic technologies for the majority of applications were being used more in warmer climates, which of course, led me to wonder why that is and why aren't these, great energy savings adiabatic humidification options being used more in Canada and cold climates. And not just Canada, I mean, it applies to colder American and European climates as well. But so why, and there's some attendees here, I hope some people here know me and they can attest to how this sort of watch on adiabatics in cold climates began a few years ago. Well, and I can say that, occasionally an adiabatic application will turn another direction based on a reason like lower humidification load application. They might have higher costs for an ME or an adiabatic solution, or maybe it's just because of design criteria like the supply air temperature before humidification is just too low. So immediately people move on from it, but we're hoping to address some of that stuff today. But what became more apparent as we dug into the data is that it's not just for those other design reasons. There was a lot of fear behind things. These fear-based responses tended to derail a potential adiabatic project pretty early on. Fears like Legionella or high maintenance requirements, or maybe too much wasted water, or even that they might think it's too expensive. But so we're here today, and not to say or push, in any direction. We just want you to understand that, there's not one type of humidification that's better than another. We just want to put the right type in the right application. So in this case, it brings us to energy use and energy analysis, and that's why we put together the webinar today. So to address the fears and the concerns, or at the very least, make you more comfortable with asking those questions when you're considering adiabatic for projects. So you can do that, of course, by entering a question through the chat. We'll monitor that and get to the Q&A session at the end of the presentation here. Once we wrap up, Nuno and I'll go through the questions. And I said his name there, so now that I said it, I suppose it's time to introduce you, good sir. This gentleman, he received his Bachelor and Masters of Engineering from the Technical University of Lisbon, and his double PhD from the Technical University of Denmark and National University of Singapore. His studies and research have always been focused on mechanical engineering and building science. He transferred from Condair, Switzerland to Condair, North America in 2018. He has several years of experience in humidification, including a heavy emphasis on adiabatic technologies. He's raised in Portugal. He loves to travel the world, biking to beaches and take down an oyster bar like no one else. Ladies, gentlemen, everyone else in between and beyond, if it's through your laptop, your phone, your earbuds, etc., please allow me to introduce the wonderful Nuno Silva. Say hi, Nuno.
Hi, everyone. I hope you enjoy the webinar, and thank you, Dave, for the introduction, and let's get started.
All right, we'll do. Okay, so first slide here. We'll just briefly go over some quick slides for the humidification world here. So this is sort of to set up the meat of the presentation, if you will. So like here, this slide, how today we're going to use terms like absolute humidity and relative humidity, which are both terms used, of course, when referring to our world. But they do have their differences. So you can see that humidity is the quantity or the amount of air vapor in the air, and that the vapor is measured in terms of absolute or relative humidity. So absolute humidity is the mass of water in a certain volume of air, expressed as grains of moisture per pound of dry air or grams per kilogram, where relative humidity is, or RH as we refer to it a lot, is the amount of that water vapor in the air relative to how much it can hold at a given temperature. All right, next slide, please. So as far as humidification goes and the energy involved in getting that humidity into the air, it's the same for either steam or adiabatic, and we'll get into that. So either way, it takes about 1,000 BTUs to change a pound of liquid water into vapor, okay? So if we're talking steam, then it takes 1,000 BTUs of electricity or gas to convert that water into steam. If we're talking adiabatic, it's the same. It still requires 1,000 BTUs to convert that liquid water into vapor. The difference is where that energy comes from. So instead of electricity or gas, with adiabatics, it uses the energy in the air, but it's the same amount of energy. All right, next slide. So here is trying to show what causes dryness. So, explain the effects of temperature on absolute humidity and relative humidity, and how that causes dryness. So you might have seen it explained with two different size glasses before, right? This slide's a little maybe modern or fancier, if you will. We're just using rectangular glassware instead, but the concept is the same. So the top left shows how if you take 0 degrees Celsius or 32 Fahrenheit air with 2 grams per kilogram of moisture, 14 grains per pound, you get 53% RH, 53% relative humidity. So we take that air indoors and you heat it up, of course, right? We bring it up to, let's say, 20 degrees or 68 Fahrenheit. The moisture content, it remains the same at that 2 grams per kilo, but the amount of moisture in the air relative to the temperature then drops to 14%. So if you look at the bottom left picture, it kind of shows how much moisture is going to be required to get that 20-degree air or space condition up to the lower end of the recommended 40 to 60% RH level. So you can see, if you take your 8.5 grams minus 2, you end up with a difference of 6.5 grams, or I think it's 45 grains per pound of air. So this becomes your load, if you will. And on the top right, a different visual on the effects of temperature on relative humidity. It increased, if you increase -5 Celsius or 23 Fahrenheit saturated air to 15 C, 59 Fahrenheit, it lowers the RH to 24%. And then in the bottom right, it's really to show how your RH, or your relative humidity, after heating that outdoor air, how it, if you start, let's say, around -18%, so this is the example in the blue squares there, -18 Celsius, that is, about 0 Fahrenheit, and you're at 50%. You heat it up to 21 C or 70, and it lowers the RH to just about 3%. So that heating, of course, has a big impact on relative humidity. So we're talking about that effect. So what are the effects on humans when we're heating this outdoor air and lowering the RH levels, right? So when the temperature is fine, we can feel it right away. Our bodies have their own thermostat, and we know when the temperature is right. We can feel it, and our partners can't sneak behind us and adjust the stat, right? The thermostat in the house, but anyway, we can feel it, but we can't always sense the relative humidity the same way. It's not immediate for us. The impacts tend to have longer, more lingering effects, like dry skin or dry eyes, right? Like those pictures. And did you know it's been proven? So that brain image there, lower RH levels actually impact your cognitive thinking ability. There's a couple of studies that I'm sure, if you're in this world, you'll see, and hopefully you'll see another webinar or two. Maybe you've seen Dr. Taylor speak to it, but yeah, it has impacts on your cognitive thinking, and then of course, your immune system isn't as responsive, and the cilia in your throat wilt, etc. So all of these different effects play on us, and we won't really get into COVID today. That's I promise it's a COVID-free zone, but we'll save that for another day. But it's clear that the message is there. The positive effects of proper humidification. That message is now getting it to do. So now we know why, right? And I guess the question here is how. So I only spoke so far about health reasons in that last slide and before, but there's other reasons like processes or energy and sustainability reasons, which we'll get into. But so here we're just trying to address the how, right? So you can kind of see the natural sources of humidification, like evaporative humidification here over, whether it's Lake Louise or Le Fleuve Saint-Laurent, or maybe atomization in the Atlantic provinces, or the Pacific Ocean smashing into a rough coastline, or even isothermal here, this natural process of a hot spring or a geyser. But we can't do that. We live 90% now, or we spend 90% of our time indoors now, so we have to recreate this inside. So how do we do that? We need, of course, humidifiers. So next slide, please. So there's two types of humidification, really, isothermal and adiabatic, and they come in various shapes and sizes with their own features and benefits. Isothermal steam is created from either your energy sources, electricity or gas, while evaporative humidifiers use different methods like evaporative media, high pressure nozzles, or ultrasonic, where the energy comes from the air, and that's where we're going to concentrate on today. Not really the products or features themselves, but where and why we should use them. So here's a visual of adiabatic offerings. There are various, you can see there's a lot of different types of it, and you might end up using, depending on your application, your building design, etc. It could be evaporative media or a high pressure system inductor in space, or even a hybrid solution because you're short on real estate or need maximum efficiencies. We might not get into those details today, but whatever adiabatic tech ends up being used, it doesn't really matter for this presentation. What matters is that we're applying the right adiabatic technology to the right application. So here's where I pass the conch on to Nuno to get into some psychrometrics.
Yeah, so like my colleague Dave was saying, we have two different types of humidification. Basically, we have steam and adiabatic. The difference from the adiabatic compared with steam is actually you will remove the energy to change the phase from the air. So if you look on this psychrometric chart, on red you'll have a typical steam process. The temperature is more or less constant. You'll get maybe 1, 2, 3 degrees, but you can also assume it's a constant temperature process. Well, the adiabatic process, as most of you know, is a constant enthalpy process, so the enthalpy doesn't change. So you can see in the blue line, when you start to humidify, you're going to increase your absolute humidity, but you also decrease your dry bulb temperature. So you always get a lot of cooling. So that's why many times when people also talk about adiabatic humidification, they call it evaporative cooling, because you get this free cooling. So of course, because of this process, the best climates always for adiabatic humidification by default is also always places that are very hot and dry. So that will be the primary best place to use adiabatic humidification, but that doesn't mean in cold climates you cannot use adiabatic humidification. And I will show you after, and Dave with some examples how we can design to also take advantage of these types of process in cold regions. One of the things also is adiabatic humidification. The more close you are to saturation, so to 100% RH, the more difficult it is to evaporate water, so the more wastewater you'll create as you get close to saturation. Also, one of the big advantages of adiabatic compared with steam is typical with adiabatic humidification solutions. You can go for very high loads, so close to 3,000 pounds an hour with single systems, while if you have steam, typically they are much less capacity systems because of the physics and the design of the equipment. But typically you will need multiple units to be equivalent to a large adiabatic humidifier. Just to give an example, for example, if you have if you have like, let's say 20,000 CFM and you have a 200 pounds an hour humidity load, if you have an adiabatic humidifier, like they say, it's more or less 1,000 BTUs per pound, you'll have a delta T, a drop of 10 degrees Fahrenheit. And you can see, for example, a big evaporative system is be around 300 watts, and they don't change much power on size, typically adiabatics, unless it's high pressure. But if you had the electric steam humidifier for 200 pounds, it'd be close to 75 kilowatts. So you can see the difference on power of the equipment and also the delta you can get with the adiabatic humidification. Also, one of the things is people usually don't talk much about this, will be what we call it in our humidification world, the equivalent COP. So typically use that for heat pumps, and other equipment, chillers, etc. But if you look, for example, on the power input of adiabatic systems and the output cooling you can get with one, you will see you can have huge COPs, sometimes closer to 100 or even more COPs, equivalent COPs. So, of course, like I say, in the winter regions, you have to be careful with the cooling. You don't want too much cooling. But if you have free waste heat and the economizer and mixing with heat recovery, you can still use this technology, like we'll show you after. Also, typically, by default, if it's less than 100 pounds, 200 pounds, it's almost like a wash compared with the adiabatic humidifiers. everything is above 200 pounds, typically always more cost effective to go for adiabatic humidification in a building. Dave, back to you.
There we go. Let's unmute. That works better. Yeah. So here we're looking at criteria for this selection, this type of a project or selection, adiabatic humidifier selection. So yeah, we know why and how. So the question is where. So here's some quick points to consider, like available space, because adiabatic often requires a greater absorption distance. It's not steam. So do you have the space available for you? 3, 4, sometimes 5 feet of distance is required. So space is a consideration. Hygienic demands, of course. Adiabatic technologies use water, so and each of them have developed their own solutions to deal with hygiene, but there's often existing water systems or maybe an existing RO system that you'll need to work with, those kind of things. So you'll need to know what the hygiene requirements for each application are. For the Canadians on board here, there could even be potential CSA limitations for certain applications, like a hospital application. Capacities, of course, as Nuno mentioned, higher capacity, anything greater than 200 pounds per hour. It's really easy to show the numbers that it makes sense to go adiabatic. It doesn't always work out that way, but and then lower loads, they sometimes need more thought as well because of just because of the comparison between isothermal but now there's lower load adiabatics. They've kind of come a long way, and ultrasonic's a good example of filling that gap. You'll need to consider accuracy, so your controller humidifier accuracy. Certain types of adiabatic humidification can be more difficult to dial in your accuracy than others. While a larger system like a nozzle system is very easy. You can have multiple stages of control, to 15 or even higher in some cases, to help you dial in through valve staging or that kind of stuff. You also need to consider service. When it comes to water, we really always need to consider service, right? And then your investment costs here. You're looking at, depending on the direction of the project, I get it. Sometimes investment costs here, it's a capital cost that you have to show up front, and it's tougher to get people on board. But if you can show the long-term payback, the return on investment, adiabatics makes sense, right? And then operational costs too, of course. And as Nuno just went through, adiabatics really do tend to win that battle quite easily through energy analysis and comparison there. So yeah, and then on the right side you have the first point. It's your electric power. If your building doesn't have electricity, I don't know where you are. Maybe we should move on from that project. But yeah, you're looking at what's available: electricity, gas. Maybe it's a existing pressure steam application for direct steam or live steam. So you have to compare all of these different things, right? And then we have to look into, with the design consideration, your preheat, is it available? And as Nuno touched on, the coefficient of performance there. And in the bottom there, I could get into water, but we all know water is pretty important. You do need to know what kind of water you're dealing with on a site. So these are good criteria that you do have to check into when looking at an adiabatic project. All right, so now we're going to get into some of the fear-based things that I brought up here. So if I go back to the fear thing, mold is a big one. Mold comes up. It's sort of a big fear for, especially older homes or older buildings. And there is definitely truth behind that. The truth is, if the building is older, it has older windows and poor insulation, maybe then, yeah, you will need to pay more attention to your indoor surface temperatures and your indoor temperature and your humidification level. Where, because if we go high, then yes, condensation could absolutely occur. If the surface temperatures are below the dew point, right? And so there's ways to deal with it. We thought it would be important to discuss it and distinguish. It's not an excuse. It's not, the intent here is to get rid of the fear. So I just wanted to make the point that when it comes to mold, well, liquid water is the only thing that can support mold and the growth of mold, right? So vapor or water vapor can't, it just doesn't work that way. So you need that liquid water. And buildings are getting smarter, better insulated with more technologies in all areas of construction, like design controls and maintenance. But when you have an older building, perhaps with single pane windows, you'll need to consider these factors. So in those cases, here in those cases, you will want to avoid prolonged exposure to areas greater than 60%, and you want to minimize trouble areas like cold piping or how condensation can maybe be avoided altogether with proper insulation and good vapor barriers. So in the next one, Nuno is going to touch on the myth of mold.
Yeah, so like Dave was saying, this is mostly important for the topic today when it's winter regions, like especially northern territories, Midwest, Canada. So nowadays, new buildings are improving the insulation, so the vapor barriers. So we are seeing less and less issues, but there's still a lot of retrofits happening and renovations, etc. So it's an issue. So like Dave was saying, if you have humid air, even if it's 60, 70, 80%, that will not create mold to grow. So what always will make mold being on the surface or even inside the wall is if there is water, so physical liquid water, because that will feed the mold to grow. So that's always an issue, and especially if it's an internal wall or inside the wall, it's very difficult then to remove that mold and that water is growing up. So you can see in the pictures on the left, you have a well insulation building, and then in the right, poor insulation building, and you can see the difference of temperatures on the surface. Like I say, it's a design issue, so it's and also a cost issue, like how much the materials, the quality of the materials, the way it was designed, the facades, the glass facades, what type of glass. They will show you after a graph on the glass and the importance on the winter humidification. But it's an issue for all the engineers always have in consideration. And actually, if there is already mold in the building, dry air is actually bad, because then the mold spores can spread much faster in dry air for the lungs of the people. So even if there is mold, I know it sounds a bit counterintuitive, but even if there is mold in the room, it's still better to have like between 40 to 50% RH than to have a dry air, because the dry air will not remove the mold if it's already existing on the surface. So now my colleague David will show, this is an example of single pane and double pane windows and the effect on the humidification.
Yeah, thanks. So we're really trying to avoid condensation. We want to make a nice, tasty, nutritional surface for mold. This example just shows. So on the left, it's double pane windows, and on the right, it's single pane windows. So on the left, you can see how double pane windows with an outdoor temperature of 0°C or 32 Fahrenheit, and indoor temperature range of 60 to 80 Fahrenheit won't condense until about 35% RH. So we're getting close to the recommended 40% minimum. If you compare that on the right to the single pane window, it's not even close, right? On the right side, we're looking at an outdoor temperature of only around 10 Fahrenheit, which is minus 12 Celsius. Before condensation could occur, and our interior relative humidity would then only come in at around 26, 27%. So there we're not even getting close to the 40% relative humidity, but at least there's some there, right? So that's just wrap up condensation here. So the fear it is real. You do have to consider some things, but just ask yourself, knowing now that mold will not grow without liquid water, even in poorly insulated buildings. If I use an outdoor temperature setback and maybe condensation sensors as safeties, could I hit the 40 to 60% recommended relative humidity? Yes, sometimes, but most of the time in the cold winters, like we're approaching now, you might not hit that high. But yeah, we'll get to a level that will be as high as it can possibly be for as often as it possibly can be to to help us get through these winters.
So now we'll go to probably one of the topics most people were waiting. So we'll go through several slides about the energy and the costs of adiabatic on the cold climates. So we'll focus mostly on the cold climates and the strategies, and we'll also show you some examples of buildings we actually measure the energy after we retrofit with the adiabatic systems from steam. So also one of the things before we start with the energy, so one of the things is being discussed recent years is in cold climates is to do a morning prehumidification. So sometimes like in the weekends or at night, buildings they tend to put setbacks and reduce the temperature and the humidity in the building, and especially in very cold climates, the humidity can drop quite a lot during the night. So in the morning it will be quite dry inside the building. So what some people are proposing is make like kind of a prehumidification in the morning. So when you start the systems, the building in the morning, like for example Monday morning, you kind of boost your just recirculate most of the air without bringing much outside air. You boost your temperature, your humidity. And also, why is that important? Because the building has lots of materials that are hygroscopic, so they will absorb all that moisture in that prehumidification before people start working. And then during the day, it's easier to maintain that good set point of humidity in the building because all the materials already absorb some moisture in the morning. So it's something, an idea for design more for the BMS and the systems of the building, but especially after setbacks to pre-humidify the building in the winter. So energy is always a big topic for adiabatic, and lots of people always say, why you use adiabatic in the winter? If you use adiabatic, you have to preheat and then you cool, so at the end is the same as steam, right? So it's true and it's not true, kind of. So like they will say, energy is energy, so you always need energy to change the phase, being from steam or being from water. Depends. The thing that changes the source of the energy, right? But typically, yes, it will require always preheat on the winter for adiabatic humidification. But nowadays there are lots of technologies in design, being enthalpy wheels or thermal wheels, so you can actually recover a big percentage of the moisture or your heat, your return heat from the building. Also, the way designed the airside economizer, which is typically in these regions, you have to be careful also not to bring too much fresh air. So there's of course always minimum fresh air for indoor quality and air quality, but always be careful how much fresh air you bring, because in the winter, the more fresh air you are bringing, the more dryness you're going to cause inside. So also it's always important when it's load size, your humidifier, to see what economizer you're typically going to use and percentage outside air. But like I say, it's very common these days to have heat recovery, especially sensitive, like temperature, like sensible, not so much latent enthalpy, but thermal wheels or cross plates, you see a lot these days on systems, and that's how we're going to get our heat, and I'll explain you in the next slides. So like I say, typically it's in cold regions where there are stronger, like cold winters, you don't typically see much like 100% fresh air. So there is always air mixing strategy with heat exchange, and also to reduce the penalty, of course. And typically, if you have a system where you have air mixing strategy with heat recovery and a large humidification, large humidification load, the adiabatic system will always pay off, and I'll show you after why. So typically, we always say if your mixing air temperature is below your supply temperature, it's going to be a wash. So adiabatic and steam will probably be very similar, and the gas humidification might even be the more advantage depending on the price of gas you have available. Also, of course, it depends what's the source of your preheat, if it's a gas heating or heat pump, etc. Depends on the COP. But typically in the cold winters, if your, like I say, if your mixed air is below your supply air, your energy between adiabatic and steam will kind of be a wash. But in your strategy, when with energy recovery, if your mixed air temperature is above your supply air temperature, like usually 55 degrees, for example, then your adiabatic humidifier will always be advantageous, because the energy you are needing for the preheat is always less than the energy you're going to need for the steam. That's usually a rule of thumb when you are designing. So if you have heat recovery, if you can have a mixed air temperature above your supply air temperature, you always go for the adiabatic. And of course, then in the shoulder seasons, the situation is completely different, and your benefits from adiabatic is even wider. So many people ask, like I say, so for every BTU I cool, I'll need to eat. So like I said, that's not true, because you're recycling your heat load from the building. So the people, the equipment, like if it's industrial, you have all the machines producing a lot of equipment, of heat, sorry, and then you can recycle that heat used to preheat, so you can humidify with an advantage. Also, your airside economizer time frame can be extended with if you have a adiabatic humidification, because of, like I say, the adiabatic cooling. Just to give an example, for example, this is a job we did. It was in northern Sweden, so it was very cold. The temperature there is quite cold through the whole year. And you can see they have two different technologies there. So they have evaporative on the left and atomization on the right. And both these systems, they have no preheat at all. So what they do is they recirculate. So it's a data center, so there is a big heat load. They recirculate most of the air. Then they bring outside air for free cooling, and then they humidify with the mixing air. But this system, you can see, this is like the size of the system and the loads, and there is zero preheat being supplied by the data center. So they always do this, and the temperatures outside are extremely cold. So they always have a strategy of mixing free cooling with humidification and the return outside air. So now Dave will show you some examples we did with the adiabatic retrofits and the savings we saw.
Yeah, so this example is in Ottawa here, the coldest capital city in the world. A downtown Ottawa office building. So there are 4 70,000 CFM air handlers operating with 10 to 15% outside air, and they were able to. It's pretty key points here is that they were able to replace 800 pounds of electric steam with adiabatic evaporative media. So the operational costs were reduced drastically, and energy savings were easy to show and were immediate. So the BAS reported lower overall outside air intake during operation, and because of the higher capacity of this humidifier and the faster response times of evaporative media for this size of a unit, it allowed for humidity reset during the evening and weekends, which again meant that they could get some savings there. And then when the regular week would come back up, the system would respond very quickly and get them back up to their design requirements during occupancy. The next one is another Ottawa job as well. Similar, but again, it's not a data center, but so they have the chiller and the pumps, the chilled water pumps, the condenser pumps, induction water pumps, etc., in the cooling tower. So the daily operational costs, you can see, were at a minimum around $800 a day. At most about $1,200 a day. But the key points here are bullets 4 and 5. So if you look at 4 and 5, with the proper design here and the input considering all the parameters, etc., this owner for 130 Slater is able to keep off their chillers for the shoulder season there of at least 2 months in the spring, from late April to late June, which resulted in over $36,000 of savings just during that time. So these sort of energy paybacks are really easy to show when it comes to adiabatic. And then a couple quick more visual slides here, and then Nuno has some more technical ones for you. But here's a visual on a building in New York City. You can see the utility rates in the bottom left corner there. We're looking at about 10% outside air minimum, full economizer, 12,000 square foot office building, 20,000 CFM air handler, and 50 tons of cooling. So through this, you can see the full all-in annual operational cost for electric on the right side there, the yellow and gray bars. The annual costs are over $13,000. And if you compare them, just go to the left side, the bar chart, you'd see the first 5 are adiabatic systems, and the average operational cost for those is just around $1,250. So it's quite lopsided when it works.
Also, Dave, this doesn't include maintenance, which typically tends to be more expensive with steam humidifiers.
Yeah, good point. Yeah. So here's another one, New York City again, just kind of on a larger scale to show you the significant difference when it's a larger project. So here, the reason why the load is larger is because they're using 20% outside air. So it's 40,000 CFM, 20% outside air. So you can see, yeah, visually it's quite significant. Gas costs are around $20,000 annual. Electric is over $77,000. And just the bottom two there, evaporative inductor in space, you can look at that, and they're less than $1,000 in annual operating costs. So the larger load, the bigger payback, right?
Yeah. So now I'll also show an example, guys. So this is a winter example. So it's actually adiabatic humidification in space. So we actually will spray the water on the space itself. So it's not very common in North America to see still systems like this in the offices. In Europe, we already see a lot of some technology spraying water inside the space. But in North America, we use this a lot for industrial applications where typically we are big heat loads. So I'll show you 3 slides. So with two different situations. So let's say we have an industrial building, can be any type of building or warehouse, commercial, whatever, and you have 100 kilowatts of heat you need to remove. So if you don't have humidification in the building, so the winter outside, the conditions, let's use a standard condition, 14 Fahrenheit, 80% RH. So you have enthalpy of 4.7. The enthalpy, we are supplying air at 65 Fahrenheit for this case with enthalpy of 17. So we have the heating of the air from the outside to inside is around 12.2 BTUs per pound of hour. So the difference of enthalpy between in and out is 1.7 BTUs. So I know it's a lot of information, but then you will see the presentation so you can go through more in detail if you want. And the ventilation to remove 100 kilowatts is around 341,000 BTU an hour. So when you remove that by the difference of enthalpy, we get around 200,000 pounds of air per hour. If we convert that to CFM, so we'll need around 45,000 CFM to remove that heat. That will be around 10 kilowatt fans for ventilation. So it depends on the system design, but let's assume 10 kilowatts. Then for the heating of the outside there, for that we are bringing in, so we have 12 BTUs, the difference, like I say, between the outside and the air you are supplying. So that will be around 721 kilowatts. Let's assume we use heat recovery in this system at 80%, which is already quite good. So 80% of heat recovery from the return air, you'll get around 656 kilowatts. So your total energy deficit that you need to supply is 65 kilowatts. If you add that to the power of the ventilation you need for the air, you'll have around 75 kilowatts you need to remove that heat load from this building. So like I say in the beginning, this is a winter situation with outside very cold air being supplied. Now let's assume you actually have an adiabatic system in your room and you are humidifying and cooling and getting to a set point of 55 RH inside the room with 72 degrees. Also, I didn't say the previous examples, also 72 degrees inside. So the same for the heating area of 12.2 BTUs per pound. The difference of enthalpy, 10.5 in this case. The ventilation to remove will be 341,000 BTU also. But now when you divide, you get 32,000 pounds of air per hour. So when you calculate the CFM in this example, you need to bring from outside to remove this load, you'll have only 7,000 CFM. So the ventilation requiring for this example goes from 10 to 1.5. But more important than that is the heating. So the heating, so you have your 12 BTUs multiplied by your pounds, 32 pounds of hour, and you get 117 kilowatts. So let's assume also we have heat recovery in this system, just sensible heat. You'll get 107 kilowatts. You subtract, you only have 10 kilowatts in this example. So unlike your previous example where you don't humidify, that was around 75. In this case, when you are humidifying your room, and don't forget, like I said, this is a winter condition design, you only need 10 kilowatts for the heating. Then we have, of course, we have the humidifier itself. So there is a water need for humidification. We can calculate based on the pounds per hour on your load. You'll need around 258 pounds of water per hour. So the power of the equipment for this will be around 1.5 kilowatts. So if you add everything all in, you have 13 kilowatts. You need to remove 100 kilowatts of heat. So you can see in this example, even if in a very cold winter condition, if you humidify your, of course, in this example, you have a big heat load also, so it changes, but you only need 13 kilowatts to remove that compared with 75 kilowatts in the example where you don't humidify. So at the end, even in this case, and that's because we always have to look in the enthalpy of the whole system, not only the look on sensible or landed, right? So you always look at the enthalpy as a whole, and you can see in this case, this will probably be an industrial application. When you humidify your building, you can get to more comfortable indoor conditions for your employees inside, so at 55 degrees, more healthy. Not only that, you also save a lot in your electrical bill at the end of the year because you need much less kilowatts to remove your heat from inside. So that was just an example I wanted to show that we do a lot of this type of jobs, even in very cold regions like northern Canada, where even in the winter you use humidification to remove the heat. Also, one thing we are not going to go through much in this presentation, also because of time, maybe another webinar we'll do. So there is a lot of green building standards these days being LEED, well, BREEAM in Europe, etc., but North America mostly LEED. And they keep the adiabatic humidifier by itself will not give you credits, so the equipment itself, but using adiabatic technologies and design, you can actually get several credits for your certification, being in energy at atmosphere or indoor environmental quality, or even innovation in design, if we had like some strategies with heat recovery, adiabatic, etc., etc. So like I said, not something you're going to go dig too much today, maybe in another webinar, but it's possible with adiabatic technologies to get several credits. And also, especially in the West Coast, we see more and more states making illegal to use steam and gas humidifiers in many applications. So more and more will be important to design and select adiabatic humidification, especially in some states. So now back to Dave.
Yeah, this one here just gets into incentives and rebates. Well, and this is specific to the U.S. In Canada, it changes with the winds or the weather. So I don't have a great resource at this time for Canada, but that should maybe change, hopefully, based on the recent news that they're releasing multi-billions of dollars into the HVAC world for us. But yeah, if you're in the USA, you can review and explore DSIREUSA.org, and you can check things out there for incentives or rebates. And if you're Canadian, you'll probably have to reach out to us, and we'll work on it with you to find any incentives or rebates based on your location, your province. So really, that's pretty much it. We're summarizing here. That was a lot of adiabatic information, not really Condair specific, so just a little quick recap of who we are. But the North American headquarters, we're a worldwide organization with North American headquarters based in Ottawa, Canada, where the factory is, where I work out of, but I'm working out of home, as you can probably tell. Nuno's at the factory. We offer a complete line of humidification products, a wide range of adiabatic products for evaporative solutions. We can help you out with lots of tools and software. More webinars like this will be coming up, and we offer full-scale service programs. So you can talk to us about those things. Let me move ahead there, please. You can find us if you need to look for us. There's a couple things, just, I mean, social media, you'll find us everywhere on social media, in particular LinkedIn. And if you're looking at LinkedIn, maybe just keep an eye out for things that are coming up in the future. And that's a webinar in January with Dr. Stephanie Taylor on healthy buildings. So that'll be January 12th, 2021. We're there, it's 2021. Let's hope 2021 is better than 2020 for our sanity. But whatever happens, we'll keep doing the right thing and implementing the right strategies and solutions, and technologies that we have to do our part in saving this crazy but beautiful world. So that's it. Again, I'm Dave, the Northern Regional Sales Manager, and on behalf of my oyster eating colleague here, my friend Nuno, and everyone else at Condair. We're gonna, before we get into the questions, usually things wrap up pretty quickly right after that. So I'll just kind of say the send off right now, but wish you all of you, your families, the best of health and happiness for the upcoming holidays, and look forward to working with you on some quality adiabatic applications in 2021.
Thank you, Dave. So I'll read some questions. I already see some guys have some questions. If you have questions, just put on the chat or on the side. There is a questions menu. So someone is asking about adiabatic humidification for hospitals in Canadian hospitals. So right now it's still not possible in Canada to use adiabatic humidification in hospitals. In US it is. We are working on that, so we expect maybe in 1 or 2 years we can see maybe hopefully some change. So we are there are lots of people lobbying for that change, especially because the equipment has changed a lot in recent years. It's completely safe these days, our equipment. So it's something we are working on, and hopefully we'll see a change in the future. Yeah, so lots of people are asking about the presentation. Yeah, so the presentation will be shared, so everyone will receive the presentation. So Condair will send a follow-up link, also a recording, I believe. Then someone is asking, it is possible to incorporate evaporative cooling with clients in certain applications. It is, but always depends. It's like we say in Condair, we always do case by case, almost like every project we do, we go through the psychometrics, we see what's the technology being used, how much fresh air is coming, sometimes people even humidifying and dehumidifying the same building I have seen before. So it's possible. It's not the most common, but it's possible. It always depends on the design behind the usage of the adiabatic humidifier. Someone is asking, should the water be treated for adiabatic humidification? Yeah, so most adiabatic humidifiers, you need to use RO water. The only ones you can use any type of water typical is evaporative systems. So in evaporative systems, we didn't discuss it much here. There is a wet media, so all the scaling and all the minerals, they don't evaporate, so they'll deposit on the media. So what happens is after 2, 3, 4 years, you replace that media with a new media and you start over again. But for all the nozzle systems, ultrasonic, etc., typically you always need to have treated water, typical RO water. DI can also be used, but you don't really need for these applications. Someone is asking if we have a calculator for predict condensation patterns indoors. Right now we don't have. Something is actually on our one of the things we want to implement possibly 2021 with other tools that will come soon. So in 2021, there is we call it a help software from Condair. You can go there and you can actually make real-time simulations and see all that type of parameters, but it's not implemented yet, just in 2021, probably like Q2, Q3. What else? So someone is asking about water consumption and sustainability. Yes, that's an issue sometimes, but it's mostly for data centers because it's huge amounts of water. But if you are using, for example, humidification with several adiabatic technologies we have, the wastewater is minimal. So all the water you are putting, if your design is well designed, you can actually use that water for humidification. So at the end, there is no negatives of the adiabatic compared with steam, because the steam also have to boil the water for that set point. You can have a very bad water consumption, for example, if you are always humidifying close to saturation or not enough preheat, and then you have, for example, 30-40% of wastewater, then yes. But if you do your design properly, then you don't have any issue with water consumption sustainability. If you use it for evaporative cooling, yeah, if you want a lot of cooling, you're going to use a lot of water. So at the end, but you can also always say all the water you evaporate for cooling goes to the atmosphere. So in the Earth cycle, let's say that water will come back again to Earth. So you're not wasting it, right? So if you evaporate that water, you get the cooling, but the water didn't disappear, right? So that's the energy balance at the end, it's almost a wash, right? So someone is also asking if there is a technical forum where I can get latest documentation. So we don't have a technical forum, but to our websites, if you Condair.com, or being in North America or Europe, there is a lot of documentation there. All the manuals are public. We have lots of white papers, case studies. So everything is public, so anyone can download that. So you don't need any login, etc. If you want more detailed, specific information, let's say I want a case study in my location or my region, then you might need to contact our representatives or Condair itself. Let me see. Some people are asking what if there is a lot of outside air coming in. So yeah, so if in the winter, if we have a huge amount of outside air coming in and the air is quite cold, likely your mixing air will still be below your supply air. So you need to use a lot of preheat. In that case, and typical will not be more than 2 months, maybe 3 in some regions, you will not have benefits from adiabatic humidification compared with, for example, gas humidification. But then don't forget, before and after that winter, you have the shoulder seasons in spring and autumn, where the temperature start to change and you can still have the benefit of adiabatic. But every case is different. So there will be regions where the payback is probably 1 year, other regions might be 4 or 5 years. It really depends on the temperature and outside air, which is true. If you are bringing, for example, 100% outside air, you have a big penalty in energy. Then also depends what type of energy recovery you have. If you have an enthalpy wheel, it will be better, but it's true, yeah. So, but then don't forget there is the also the shoulder seasons and summer. You can also even have evaporative cooling depending how is your HVAC system working. Someone asking about the risk of Legionella. Yeah, so our systems, all our adiabatic systems, so we don't launch or we don't sell any system without being with measures to avoid any issues with Legionella. So most of our adiabatic systems, they always have active technologies to kill any bacteria. It can be silver dosing, for example, submerged UVs on the water, flush cycles, drain cycles, no recirculation. So we always do a risk analysis in our systems to make sure that that we don't have any issues with Legionella. So I always used to say, people, when you have a humidifier from Condair, never turn it off, leave it on 365 days a year, and you'll do all the flushing and cleaning, etc., etc., and every day to avoid any old or stagnant water. Someone is asking if there will be credits available for this presentation. I'm not sure. I need to ask our marketing people, but I will follow up with that and will inform everyone. Someone is also asking the presentation, so we already replied. Yes, the presentation will be shared with everyone. How to get energy simulation. So right now, if you want the energy simulation for your location, you'll need to go through our reps or contact Condair directly, and we'll do it for you. We can do hour by hour energy simulation for the whole year, and then we'll discuss with you guys what type of design you have, what technologies you have, what's your COPs, etc., etc., and you can put all that data and generate a report for your adiabatic humidification and compare it with other technology like steam exchange, gas humidification, etc., etc., and show you a 10-year total cost of ownership, for example. What else? Recirculation. No, so the only system, so someone was asking if to recirculate the drain water. So the only system with water recirculation is actually evaporative media. And that water is in like a tank, a stainless steel tank, so not the drain. So the drain water is always to drain. But yeah, in evaporative systems, we typically recirculate the water. But in other types of adiabatic systems, they are demand systems and typically will never recirculate the water, and that's also for hygiene reasons. We always want clean and fresh water to be in your airstream. DI water, yeah, so someone is asking, can we use DI water? Yeah, DI water is usually possible to use with adiabatic humidification. Only technology where I don't advise to use DI water is evaporative systems, because typically the media, there is the glue that bound the fibers. It can start to get damaged if you put ultra pure water, like 18 megaohm water, for example. It can actually corrode that that medium. I think that's all, Dave. We are on time exactly, so 2 o'clock.
Yeah, 2 o'clock, a lot of information. Thanks for hanging in there with us. Yeah, check out the presentation for any details that you want to look further into, or feel free to contact us. It was our pleasure. Thanks everyone very much. Thank you, Nuno. Great work as usual. And
Thank you, everyone.
We'll see everyone around. Take care.
Thank you, everyone, and thanks for your time and for joining us today. Okay, have a good week.